Hi, welcome to the third video in my series about CPU architecture. Um, and in this video, I assume you've watched my previous two videos dealing with really the role that the ALU and the control unit have in general within executing instructions in the CPU, as well as the different registers that are in the CPU and their role and function and what each one of them is connected to. As discussed in the previous video, we're going to be working with a hypothetical instruction cycle. The actual clock ticks will be different depending on how the CPU has been designed or thought out. It depends on many things. But to keep it simple, remember it's a model, and so in this particular model, we're going to assume that we need one clock tick to do a fetch cycle. We need two clock ticks to do a decode cycle, and four CPU clock ticks to do the execute part of the instruction. So the entire instruction will run through in 5 CPU clock ticks. What's a clock tick, you may ask? Well, it's really the shortest period of time that the components within the CPU need to settle and respond for the circuits, the transistors to stabilize and reach a stable state. And again, that depends on the technology. If a CPU has a higher speed rating, it means that it can respond much faster, that its transistors work much faster, and therefore the clock tick cycle, the clock tick for that particular CPU is therefore much smaller, so it therefore executes the instruction much quicker. Right, we're going to do a very simple instruction trace. We're going to assume that we have in memory an instruction at address location 23, and that we have a variable x stored at address location 12. So we'll begin with the instruction read cycle. We assume that there's been some other instruction that's busy running, and that's sitting in the IR. So we now begin the process of fetching the next instruction. So the address of the next instruction will be sitting in the program counter. That will then be pushed into the memory address register. The memory address register will push this out through the address bus and locate and gate onto address number 23. By the way, the instruction incx will actually just be a binary number. It's just a binary string representing the incx instruction, and that binary instruction will, or machine code, will be loaded, pulled in from RAM through the data bus into the memory address, the MDR, the memory data register, and that in turn will then be gated into the instruction register, where that binary value will now sit and wait to be decoded. So, to summarize, in this phase, the program counter, the address of the next instruction that's going to be executed is loaded as the MAR. We look it up, address 23 in this case. The binary representation for incx, which means increment x, is pulled in through the data bus on a read cycle into the MDR, and then that is dropped into the instruction register, the IR register, so where it is now going to be waiting to be decoded by the CU, the control unit. Alright, in tick 2, the CPU, the way that I've designed this model, is basically the ALU is sitting here doing absolutely nothing. And the normal way that programs execute is that after you've executed an instruction at address 23, you will then move on to the next instruction, sequential execution. So the one thing that has to happen is that the program counter, remember, needs to point to the address of the next instruction to be executed. So this is the first thing that will happen. So that the ALU and the CPU wants to best utilize the time that it has. Now that we've finished loading the instruction from address 23, we can update and change the program counter value. And it does that by pushing the value of 23, which again, remember, will be a binary representation. So it pushes that binary value into the accumulator. Again, we'll store this as a binary string. The accumulator will then take that as its input. Control unit will probably be telling the ALU, hey, you need to do a +1 operation on this. At this point, it will increment it, and that will then be written back to the program counter. So in this first tick of the decode cycle, the program counter will be incremented from 23 to 24. At the same time, the circuits inside the control unit will be busy decoding the binary instruction representing IncX. You also notice at this point there's no interaction between the CPU and RAM, and it's probably at this point that the memory refresh cycle will probably be happening. So this is where the RAM is actually inaccessible, and the capacitors that are being used to represent the ones and the zeros are being refreshed at this point. And at the same time, the CPU, the control unit, is decoding and breaking down that binary instruction, and it's figuring out things like, okay, I need to increment X. Where is X? Oh, X is at address location 12. Fantastic. And so 12 will now have to be pushed into the MAR on the next part of the decode. The M data register, once I've got the value of the, once I have the value of from address 12, which is 14, I'm going to then push that into the ALU. That's what it's planning to do. So that's basically its little instruction list. Right, this is what I'm going to do in my execute part of the cycle. Right, so now enough time has elapsed and circuits are stabilized, and we can start doing the execute part of the instruction cycle yet again. So the control unit is now worked out. Okay, I need to pull in the value of X, which is in the memory location 12. So the control unit will push the value of 12 into the memory address register, and that will then look up address location 12, and the binary representation of 14, which is what X is storing, will be sitting in address location 12. That will then get pulled in through a read cycle into the memory data register. The memory data register will then be pushed into the accumulator. The control unit will tell the accumulator, hey, you need to increment the value that's in your accumulator. So it takes the binary value of 14, which is 1110, apologies, pushes it through the ALU, effectively doing a binary addition. So it's adding 1 on to 1110, and we get the result 1111, which is 15. And that result will be sitting in the accumulator at this point. And that's probably the fastest that the CPU can do it. And in the final phase of execution, the value needs to be moved from the accumulator back into the MDR, and then a write cycle takes place, and the resulting value of 15 or 1111 in binary will be written to address location 12, and that will complete the execution of the instruction IncX. And that's it. That's a very simplified view. I know it looks very complicated and sounds very complicated, and it actually is extremely complicated in reality, but that is the fetch, decode, execute cycle, doing an instruction trace through the CPU. I hope you found it interesting, if not a little daunting and confusing, and I hope it explains a great deal about how the fetch, decode, execute cycle works, and how it relates to the computer architecture and registers that you have been learning about. Thanks for watching. That's all.